Hey everybody, how you doing? Alright, welcome back. We're going to be looking today at how you use proportions to solve some geometry problems. There's two different videos for this section. In the first one, we're going to learn to use proportions to find unknown lengths, which is still something we'll accomplish in the second one, but it'll focus on scale drawings in particular. Alright, well, let's take a look at it. What I want to start off with are actually some properties of proportions that I'd like you to see work, although I don't necessarily need you memorizing these. Nevertheless, good for you to see. I've written four proportions, and I want to know which of the following proportions are true if this proportion is true: A over B equals C over D. Now, basically, I'm telling you that the ratio of A to B equals a ratio of C to D, right? Because that's what proportions are equal ratios. All right, so which other ratios have to be equal if that one's equal? And really what I want to do is I want to talk about how you can manipulate the parts of the two equal ratios within a proportion in order to make other ratios that are equal to one another all the time. All right, now let's examine each one of these proportions one at a time and see what the difference is between that ratio, that proportion, and the given one. All right, so B is to A as D is to C. Do you see what I did with this proportion in order to make this one right here? Hopefully you can see that these two ratios are simply the reciprocals of these two ratios. Now, if you just flip both ratios in a proportion, is that going to make the proportions equal, or is that going to make a new proportion? You know, if you want to try that out, just try something simple like make a proportion that you know, 3/4 equals 6/8, and then see if flipping both sides gives you another equal set of ratios. And indeed 4 over 3 is equal to 8 over 6. And I don't care about what the two ratios in a proportion are. If you take the reciprocal of both of them, you're going to have another proportion. And so this one is true. And that's called the reciprocal property of proportions in your textbook. I'm not going to write that property out, but check out page 364. You'll see it along with the other two properties I'm trying to illustrate. Okay. Now, for part B, let's see if we can determine how we made this new proportion. Well, is it a proportion or not? We're going to find out. But how do we make this new equation? Well, we put A over C equals B over D. Well, what I want you to notice is that the things that stayed the same here, A and D, are still in the same place, aren't they? But what's changed with these two proportions is the location of the means. Here, B was in the first ratio, C was in the second one, whereas here, those are switched. So we've interchanged the means. And the property in the book that we're referring to is going to tell us that that's exactly what you're doing, is you're interchanging the means of that proportion. And when you interchange a means, it turns out that you do get another true proportion. Now, let me illustrate that again using this whole 3/4 equals 6/8 thing. All right, if I were to take the means in this proportion and interchange them, I would get 3 is to 6 as 4 is to 8. Those both equal 1/2, don't they? So you see that interchanging the means within a proportion makes another proportion. So that one is true as well. Okay, well, now let's look at how I manipulated the original proportion to make the proportion in part C, or what we think might be a proportion. What I did basically is I made a ratio of out of the extremes, and I made a ratio out of the means, right? A is to D as B is to C. So I made a ratio out of the extremes, a ratio out of the means. Now, does that work to show that to make a new proportion? Well, again, let's take that 3/4 and 6/8 and kind of illustrate this. If I were to make a ratio out of the extremes in this proportion, I would get 3 over 8. If I were to make a ratio out of the means, I would get 4 over 6. Those are not equal to one another. So making a ratio out of the extremes and making a ratio out of the means does not make a proportion from another proportion. All right, finally, this one, if I had told you that there was one false one, part D is the one you would have told me right off the bat would have to be false. But it turns out it's true. I need to explain where this seemingly nonsense comes from based on this proportion first, and then I'll show you with our old 3/4 equals 6/8 how it actually is true. What I've done to get this A plus C over C, oh, you know what? I wrote the wrong thing. Excuse me, let me pause and change that. My apologies, I went ahead and made the changes in orange. Here's what I was intending to be there. What I did was I just basically took the denominator of each ratio, the B and the D, and I added them with the numerators. So I did A plus B, but I kept the denominator the same, over B. C plus D over D. All right, you see that? Now let me show you that that actually works to make a valid proportion. Let's use the 3/4 and the 6/8 again. Let's erase this. What I would be telling you then is that if I take this first proportion, I do 3 plus 4, which is 7, and I keep the denominator the same, that would give me a ratio that's equal to doing the same thing with the other side. Or if I take 6 over 8, if I add 6 and 8, and then keep the denominator the same. And indeed, 14/8 does simplify to 7/4, doesn't it? All right, so you can always just take the denominator of each ratio and add it with the numerator and get another proportion out of a proportion. That was true as well. Again, I don't need you to memorize all those properties, but if you do know them, you're a little bit ahead of the game and you'll understand why there are so many different ways of solving some of these geometry problems involving proportions. Now, I'm only going to work on one problem with you, and I'm going to kind of show you why we use all those different properties that we just talked about. What I'm telling you here to do is to make 4 proportions to find the value of x, which is this distance right there, given that the ratio of A to B, or of AB to BD right there, equals the ratio of AC to CE. Now, there's lots of different ways that somebody might go about trying to find the value of x here. One of those, well, I guess I won't even say that. All of them simply involve making ratios out of corresponding parts of the figures that you see in this picture. Okay? Now, let me try to explain that to you a little bit. For instance, if you look at AB and BD, that's like the top half of the left side of the triangle and the bottom half of the left side of the triangle. Well, it turns out that that is equal to, according to this, the ratio between the top half of the right side of the triangle and the bottom half of the right side of the triangle. And so I can make this proportion in order to find out what x is. First, I'd have to know how long the bottom side is, and the bottom side, I hope you can see, would be x minus 10, right? I could make this proportion that 8 is to 12, as 10 is to x minus 10. Okay, now I'm going to try to do this using the properties that we talked about on the previous slide, and then I'll show you in the picture why they actually work. Remember, one of the things we said we could do on the previous slide is we could make a new proportion simply by taking the reciprocal of the original proportion of each ratio. So I could make 12 is to 8 as x minus 10 is to 10, right? And I think you can see that the ratio between the bottom half and the top half of each side of the triangle would have to be equal if the reciprocal was true. Another way we said we could make a proportion out of a given proportion is to interchange the means with one another. All right, so in this case, that would involve interchanging the 12 and the 10. And so that could look like this then. 8 is to 10 as 12 is to x minus 10. Now in the picture, why would that work? Well, it's kind of intuitive. If I'm saying 8 is to 10 as 12 is to x minus 10, I'm saying the ratio between the top half of each side of the triangle equals the ratio between the bottom half of each side of the triangle. By the way, bottom half. That's not exactly what half is it, but I think you get my meaning. And the third way of manipulating a proportion in order to make a new one that we just learned is that you can take the denominator and add it with the numerator and then just keep the denominator the same. Now this is where this one will start making sense whenever you see the parts in the picture, how they correspond with one another. Well, let's just do that though. If I add the 12 with the 8, I'll get 20. And I'll keep the 12 the same. And think about this one. If I add x minus 10 with 10, well, x minus 10 plus 10 is just x, isn't it? All right, over x minus 10. Here's what I'm saying in this picture. I'm saying that the ratio between the entire left side, which is that 8 and 12 put together, or 20, the ratio between the entire left side and the bottom part of the left side equals the ratio between the entire right-hand side and the bottom part of the right-hand side. Okay? Now we even could have made one more proportion where we could have said the ratio between the entire left side and the top part, 20 over 8 equals the ratio between the entire right side and the top part, which would be x over 10. That's 5 different proportions that I could use to find the value of x, and there's still more that I could create. I'll get rid of the last one though, just because, well, try not to overcomplicate things too much. I know I've already done that a little bit maybe. Hopefully you're following me though. Alright, now every one of those proportions will give you the exact same value for x. I'm going to go ahead and show you how that works with a couple of them, and then trust your algebra can find the rest of them. But the point is, make ratios between corresponding parts of figures whenever you have proportionality involved in geometry problems, and you'll be okay as far as finding unknown lengths. Alright, so let's start with the first one that we made, that 8 is to 12 as 10 is to x minus 10. If we cross multiply, you see how we would get 8x minus 80 equals 120. Alright, and so that would give us 8x equals 200. So x equals 25. Alright, now I think you can imagine how we'd get the exact same thing if all we do is use the reciprocal part, right? So you don't need me to show you that that's going to give you 25 again. And you actually don't need me to show you that this is 25 again, because its cross products are exactly the same as we had before. 8 times x minus 10 is 8x minus 80 again, right? And 10 times 12 is still 120. So it's kind of obvious that these two proportions would give us the same solution for x that this one did. So let's use the fourth one that we made and show you that this is working out. If I multiply 20 times x minus 10, I would get 20x minus 200. And then I would get equals 12x when I multiply the means. And that again gives me 8x equals 200. So it again gives me x equals 25. Kind of cool whenever we're working with proportionality in geometry that there's so many ways of getting the exact same answer that are all correct. There are incorrect ways of doing it as well. Alright, I wouldn't have wanted to say that the top half of the left side compared with the bottom half of the right side equals the top half of the right side compared with the bottom part of the left side. That wouldn't have worked. But I showed you many ways that do work. Alright, hope this has helped you understand how you can find missing links using proportions in geometry problems. See you next time, guys.